Let's work through an example of finding our unit tangent, unit normal, and binormal vectors. I've gone ahead and written out for ourselves here what those calculations are, so we can refer to them when we need to. But it's also a good reminder as to what it is that we're trying to find. So the first part of this is to go ahead and take the derivative of our vector r of t, which comes pretty easily. So r prime of t is going to be equal to 6 10t and negative 8. Then we also need the magnitude of r prime of t. And that's going to be equal to the square root of 36 plus 100t squared plus 64, being careful to square the negative with the 8 here. And that ends up turning into 10 square root 1 plus t squared, or t squared plus 1. So pretty quickly we can get to our unit tangent t. That's going to end up with a vector that looks something like this. 3 over 5 square root 1 plus t squared, t over the square root of 1 plus t squared, and negative 4/5 square root 1 plus t squared. So there we have our unit tangent, and that comes again pretty quickly. The normal now is going to be a little bit more work. Actually, it's going to be a lot more work if we're going to do it generally as a vector function, because now I have to find the derivative of this vector function and divide it by its magnitude, which does and can get quite complicated. So probably what makes more sense for us is to put this into a computer algebra system, and that's what I've done. Our t prime then, that we get from our computer algebra system, is going to look like negative 3t over 5 times t squared plus 1 to the 3/2, 1 over t squared plus 1 to the 3/2, and for the k component, 4t over 5 times t squared plus 1 to the 3/2. And I'm using rational exponents here. One's a little bit cleaner than using the roots, but also that's what the computer algebra system gave me, as well as it reversed these to t squared plus 1s instead of 1 squared plus t's. So we've got that now, and that saves us quite a bit of time. We also need a magnitude of t prime, and again, much like computing these things by hand goes, we can imagine that this magnitude might take us a while to compute, simplify down. In this case, again, I've used a computer algebra system to do that. So the magnitude of t prime of t is going to be equal to 1 over t squared plus 1. And now we've got that as well. So we can go ahead and set up our overall vector for t prime and our normal. So again, the normal vector now, and of t is going to be t prime over its magnitude. So really that means that we're taking t squared plus 1 times the vector t prime of t, and again, just foregoing some of the simplification that took place in there and getting into a form that kind of makes sense. Here's one way we could write this out. It's not the only way, but it is a way to do it. We could have the vector negative 3t, 5, and 4t, and divide that vector then by 5 square root t squared plus 1. So this can represent a way to write this out. Again, there's more than one way to express this, but it gives us something to then work with. From here then, if we want to find our binormal vector, Again, what we want to do is take the cross product of these two vectors here. And again, as you might imagine, the amount of work involved in this from an algebraic standpoint is pretty substantial. So we have to take this vector here and cross it with this vector here to make that binormal. So to make that lift just a little bit lighter, one of the things that we can do is factor out any common factors. So in this case, we can pull out this square root of 1 plus t squared as a constant and bring it out in front. And we can also do that then here with this piece as well, just so that we can make that piece of the calculation after the fact. As far as the determinant is concerned, as far as the cross product itself is determined, those will just get multiplied in back at the end. And in fact, we'll see that we get kind of a nice little benefit out of that. So if we take t to be the vector 3/5 t and negative 4/5 all divided by the square root of t squared plus 1, and we take n as we've got it listed over here as negative 3t, 5, and 4t, and divide that by, again, we've got our 5 square root t squared plus 1. Then we can go ahead and set up our cross product in the following manner. So we can write this out as 1 over the square root of t squared plus 1 times 1 over 5 square root t squared plus 1 times our cross product of the piece that remains. So for t, that would be 3/5 t and negative 4/5. And for n, that would be negative 3t, 5, and 4t. And now it's much easier to compute that cross product as we roll through it. So now let's get that. And even as it is, we can go ahead and use the computer algebra system to help us find that cross product. And I've gone ahead and done that. So this is our calculation for our binormal vector. And I've gone ahead and computed this. If we simplify down this expression here out front, the product of these two magnitudes turns into 1 over 5 times t squared plus 1, which is pretty handy. Again, computing this on a computer algebra system, I have the following vector: 4 plus 4t squared, 0, and 3 plus 3t squared. And then we can simplify this just a little bit more by factoring out the common factor here of 4 and 3 plus, or rather 3 times 1 plus t squared. And we get some extra simplification when we push in our function here. So this just all turns into 4/5, 0, and 3/5. So pretty clean function for our binormal, pretty clean vector rather for our binormal here, given that we were working with some fairly complicated functions. So now we've got all three. A lot of times when you work through these problems in textbooks, what you'll find is they'll ask you to make these computations at a specific time. And that's really just meant to simplify the process a little bit, because these derivatives and these magnitudes do get a little cumbersome algebraically. So I think allowing ourselves the opportunity to use the computer algebra system to make those calculations is nice, because it gives us the opportunity to explore these from their functional standpoint.